Intelligent Transportation Systems Podcast. Hello, welcome! I'm Javier Sanchez Medina from the Intelligent Transportation Systems Society. Welcome back to the Pinnacle on Intelligent Transportation Podcast. We have a warm new episode ready to be tasted by our selected and special audience. The central content of this issue is a fascinating and inspiring interview with Mr. Lyle Saxton, a veteran engineer in our field that has had a lot of responsibility posts. Our guests talk about very hot topics in the field of intelligent transportation, but with a privileged perspective of an extensively experienced colleague. So don't miss this one, it is really inspiring and educative. Of course, we have our regular mini-sections, a news mini-section by Dr. Kaveshgar, and a transportation and history mini-section by Mr. Shirazi. But we also have a new mini-section. We have a book comment coming from Professor Haluk Eren from Firat University, Turkey. The book title is Advances in Intelligent Vehicles. We hope you like this new content. And that's it. Lean back in your armchair and enjoy.
This is the news mini-section for episode 30, November 2015 by Maryam Kaveshgar. While more than 600 of the most brilliant researchers had gathered in Las Palmas for ITSC 2015 in September, the work on intelligent transportation system and, of course, autonomous driving was on full throttle in other parts of the world. Stanford introduced Marty, a self-driving electric drifting DeLorean. Professor Chris Girdis built this drifting automotive research vehicle in style using a vintage 1981 DeLorean. The car can autonomously make precise donut circles at a large drift angle. Soon will be capable of using the same technique to take tight turns around the obstacles on the racing track. The paradigm of the lab is that an autonomous car has to be able to handle all different critical conditions and not only simple situations. Ironically, the news of Marty was reported on 20th October 2015. Back to the future, anyone? Company Tesla offered an update to its software on Model S, allowing the use of autopilot. As it was mentioned on their website and their blog, the update will allow the car to steer within a lane, change lanes with a simple tap of a turn signal, and manage speed by using active, traffic-aware cruise control. Tesla started equipping its Model S last year, October. However, the internet is bombarded by footages posted by people showing that how Tesla's autopilot is failing and rolling out everywhere. Virginia Tech automated vehicles drove themselves in the 95 expressway. Of course, that Monday, 19th October, the roads were closed to traffic. The project staff watched the cars real-time on live video cameras. The demonstration featured an automated vehicle performing lane changes and automated braking in response to different driving scenarios, like a simulated work zone and an approaching law enforcement vehicle. As a side note, please be aware that the Intelligent Vehicle Symposium 2016 call for papers has been published. It will be held from June 19th to 22nd in Gothenburg, Sweden. Please check this episode's post for details at ITSP.cicei.com. Stay tuned for the next month's news.
Transportation in History by Mehran Shirazi, PhD candidate at Simon Fraser University, Canada. History of police cars. Police forces began using motorized vehicles sporadically as far back as the final years of the 19th century, but at the time, these were little more than wagons that carried police from place to place. Police forces used motorcycles on a regular basis long before they used cars, as cars were more expensive. Increased reliance on police cars was driven primarily by increased use of cars by criminals. In 1899, the city of Akron, Ohio, paid the Collins Buggy Company $2,400 which is about $65,000 today, for a battery-powered wagon. America's first horseless police vehicle left a lot to be desired. Weighing about 2,300 kilograms, it had a top speed of just 25 kilometers per hour and a range of 48 kilometers before the batteries had to be recharged. This car was later trashed in a riot. The city never bothered to build a second one of these police vehicles. Although these electric wagons were faster than human and horses, since they did not have any means of communication with the HQ or the other police officers, they were not very effective. The thing that made the difference was the two-way radio. This apparently plain gadget allowed police cars to really take off. With a car and a radio, one officer could cover a much larger territory. During 20s and 30s, cars were purchased retail and then modified by the police department. Modifications were limited. Simple markings and a variety of lights were the only things that set most early police cars apart from regular cars. It wasn't until after World War II that the big three, Ford, General Motors, and Chrysler, began to offer specialized, more secure and effective police packages. Ford's introduction of the Ford Flathead V8 in its Model B in 1932, the first low-priced, mass-marketed car with a V8 engine, gave it brand loyalty that allowed it to capture the police car market until 1968. In 1969, Plymouth took first place in the police market, with Chrysler's Corporation's 440 cubic inch V8s, torque-free transmissions, and torsion bar suspensions giving them a compelling advantage. Chrysler held their lead until the 1970s oil crisis drove buyers to smaller cars, and Chrysler discontinued their rear-drive platform after the 1989 model year. By early 1980s, big engines were nearly extinct and police departments had to turn to likes of Ford Fairmont or Plymouth Volare. Most of the police spec vehicles were the same with the ones built for taxi use. Although gasoline-powered has been the overwhelming choice over the last century, the electric police car is making a comeback. In 2007, an all-electric police car debuted in Pennsylvania. At the end, let's mention some of the nicknames police cars have picked up during these years. Some of the most amusing British terms include the fuzzmobile or jam sandwich. In the UK, police vans are known as meat wagons, while in the US this term refers to an ambulance instead. In the UK, police cars used for patrolling are also called panda cars, named as such because they were originally painted black and white. What are some nicknames for police cars in your country? Let us know.
This is the book review section for the present issue of ITSPodcast, reviewed by Dr. Haluk Eren Firat University, Elazig, Turkey. The book title is Advances in Intelligent Vehicles and consists of 320 pages, edited by Yobin Chen and Lindsay Lee, and published by Academic Press elsewhere in 2014. This is not a textbook for undergraduate students, but a book for ITS researchers whose chapters are prepared by different authors. The book combines some of prominent topics of intelligent vehicles via simple or advanced models. As known, there is a new ITS transaction entitled Intelligent Vehicles that will be published as of 2016. For that reason, researchers may more focus on IV technologies as reading the present book. This book embodies advances in intelligent vehicles, prompting new advancements of research and development in IV technologies. This emerging field improves the safety, reliability, and performance of vehicles, vehicular networks, and systems. New technology vehicles can be equipped with multiple sensors and sensor networks in a complex driving environment, with high-level interactions between vehicles and infrastructure. According to the book perspective, semi-autonomous or autonomous driving can be considered as intelligent vehicle systems. The goal of this book is to introduce state-of-the-art technologies for IV systems. As reading the book, researchers and engineers may get most recent research information. Also, the reader will get clues about the overall system of intelligent vehicles as a cyber-physical system. 10 chapters take place in the book. All the chapters are prepared by eminent ITS researchers. Great deals of significant topics in the IV research domain are included in the book. In chapters 1, 2, and 3, authors deal with different designs and testing platforms of intelligent vehicles. Chapter 4 handles collision avoidance. Chapters 5, 6, and 7 mention about human factors and driver behavior. Chapters 8 and 9 elaborate driver assistance systems. Last but not least, Chapter 10 provides the research details of an active safety study. The book thoroughly discusses the latest technologies emerged in intelligent vehicles. This may cause researchers to get new horizons and enable them to see the future research trends of IV. Let's briefly look at the highlighted points of the chapters. Chapter 2 consists of 20 pages, and it is written by Arda Kurt, Michael Vernier, Scott Biddlestone, Kate Redmill, and Ümit Özgüner. It deals with procedures and tools employed in the testing stages of the intelligent vehicle design. This work exhibits a methodology utilizing both simulation environments and small-scale indoor test beds before the outdoor tests. Using sensors, agents, scenarios, and environments, the benefits of virtualized subsystems for the entire series of tests are exposed with demonstrative examples. Each stage of the testing process is performed at the Ohio State University Control and Intelligent Transportation Research Laboratory. Chapter 3 consists of 23 pages and written by Dai-Heng Ni. Author presents mathematical modeling for connected vehicles, communicating with each other and roadside. The aim of this chapter is to provide a theoretical basis for modeling connected vehicles on virtual environment. It exemplifies the design and test with applications and exposes strategies integrating by connected vehicles on the basis of field theory. This approach is given with sample applications such as VANET Simulator. Many descriptive plots sketch the matters residing in subsections. Chapter 4 consists of 21 pages and it is written by Eric Rodriguez Seda and Dusan Stepanovi. Their focus is on the collision avoidance problem for autonomous vehicles and develop strategies to guarantee the avoidance of a dynamic obstacle. 2 examples are introduced dealing with the performance of the control schemes. Non-cooperative and cooperative strategies are handled to guarantee collision-free trajectories for a 2-agent system with actuation constraints. They build a control structure via avoidance functions with a heuristic solution to get away deadlocks and traps. Chapter 5 consists of 48 pages and Chapter 6 includes 39 pages. They are both written by Jianqiang Wang, Keqiang Li, and Xiao Yun Lu. Chapter 5 emphasizes the effect of human factors on driver behavior and analyzes the differences in subjective evaluation and objective experiments. Authors talk about the effect of human factors on driver behavior and development of a simulator. A comparative analysis of the differences is performed by the driving simulator and the real-world environment. Chapter 6 investigates the effect of out-of-human factors on driver behavior profile, such as vehicle, road, environment, and traffic. Here the terms and scenarios are consistent with those in Chapter 5. Due to the complexity of human driver characteristics, authors address the difficulty of its modeling. The test vehicle in Chapter 5 is also being used in the experiment. Chapter 7 consists of 24 pages and it is written by Dana Prokaskova. The addressed issue by the author is human factors for safe human system. This ensures the continuity of limited infrastructure operation with human survival. Herein a reader discovers the role of human rationality, coordination, experiences and perception under different working conditions. Author handles the integral risk of the human factor in both management and engineering activities. Chapter 8 consists of 33 pages, and it is written by Chunzao Guo, Seiichi Mitai, and David McAllister. Authors present a robust vision-based road environment perception system. It can be used for navigating an intelligent vehicle through challenging traffic scenarios. They discuss utilization and integration of traffic evidences and geometric clues. Also, temporal supports of the rule scenes are provided for the detection and tracking of the objects in probabilistic models. Chapter 9 consists of 30 pages, and it is written by Jianqiang Wang, Jiaxi Liu, Xiaohui Qin, and Keqian Li. The chapter handles V2I-based multi-objective driver assistance system for intersection support including safety and congestion. It focuses on a study and a configuration of the intersection driver assistance system and the algorithm of multi-objective system. It composes of two functions that are driving support and traffic signal violation warning. The effects of this system on intersection driving are analyzed by random traffic simulation and field tests. Chapter 10 is the final and consists of 29 pages. Fang Chen, Minjuan Wang, Lian Duan are the authors. They talk about technologies and challenges related to the design of a human-machine interface for ADAS to meet the dynamic requirements of drivers in different traffic scenarios. Here these several methods are introduced with the aim of predicting stochastic events in traffic and preparing to take correct action. This book shares results of scientific studies and findings. Also, it promotes feature research. Most of the chapters are supported by explicit mathematical principles. At the start of each one, reader can find the outline of it, while the references are recited at the end of each chapter. The intended readers of the book include professionals, researchers, and graduate students who are interested in recent advancement of research and development in intelligent vehicle technologies.
Hello again! It is now time to jump into our today's interview with Mr. Lyle Saxton. We hope you enjoyed this one as much as we do. I personally enjoyed every word. Hello, I'm proudly introducing Mr. Lyle Saxton. He's a reference in our field and he has kindly accepted joining us today. Mr. Saxton has occupied quite a few of high responsibility posts. After joining the Federal Highway Administration in 1968, Mr. Saxton worked on vehicle highway communications, in-vehicle navigation and information, traffic and freeway management, and automated vehicle control. He became a recognized leader in developing national and international support for intelligent transportation systems and technology. He was moderator of the two National Mobility 2000 workshops, composed of key national leaders in government, industry, and academia. In 1991, he received the Transportation Research Board's Roy W. Cram Distinguished Service Award. He was also the general chair of the very first IEEE International Conference on Intelligent Transportation that was held in Boston, Massachusetts, back in 1996. Now, just a few weeks ago, he has been given the IEEE Intelligent Transportation Systems Society Lifetime Achievement Award at the 2015 edition of such conference in the Canary Islands, Spain. Mr. Saxton also received last year at the ITS World Congress their equivalent award, so it seems to be a consensus on his contribution to our field. Hello, Mr. Saxton. How are you? Thank you very much for joining us today. We're honored. Can you please introduce yourself to our listeners?
Well, good morning to you, Avi. And I want to thank you certainly for that gracious introduction. It's my pleasure to join you and to join your listeners in this area of discussion on intelligent transportation systems. So I look forward to our discussions.
Good. Mr. Saxton, during the last ITSC 2015 awards ceremony, you were kind enough to show us 3 pictures we are sharing in this podcast website. I recommend our listeners to watch them carefully. They were 3 front pages of 3 different journals in 3 different epochs, right? Do you want to talk about them?
Well, I showed those pictures, Javi, because I felt those publications played an important role in the earlier days of ITS. And actually, as we all know, it wasn't called ITS then, but it certainly evolved into it. So let me set the stage a little bit as to how those publications came about. I'm an electrical engineer, certainly, and I was recruited by Federal Highway in 1968 to develop a more substantive advanced electronics capability within the Federal Highway Administration. I had actually come from about roughly 10 years of experience in the space business before I got into this area of transportation. And so I had been able to see, like anybody else in that area, the very many opportunities that modern electronics offered. So when I came over to Federal Highway in '68, I sort of looked around, if you will, and I saw that, some research and similar type of technology development was going on, but it was kind of scattered in this area of highway electronics, and it was not well known as to who was doing what. So we actually felt that one of the important things we could do in those early days was to try and establish what the state of the art was, and to get people involved who actually were doing research and give them a forum in which they could basically publicize some of their activities. And so, being an electrical engineer and working in the area of highway electronics, we said, well, it's obviously going to be the IEEE, and we set out and developed a partnership there with the Vehicular Technology Group. And I offered to be the guest editor, and they offered to allow us to prepare a complete special edition of the Vehicular Technologies transactions. And so we actually invited the authors, we peer-reviewed them, and in 1970 we came out with this special issue on highway electronics. It was really quite successful. We had 19 peer-reviewed papers. We covered the waterfront, and it might be surprising to look back then, and you might think it was the dark ages, but we actually had articles on vehicle detection and highway communication, even in-vehicle route guidance, as well as automated vehicle control. And the Federal Highway bought extra copies of these of this special issue, and we distributed it pretty widely to universities, to industry, to state and local government. So in our opinion, that was pretty successful, and I think it demonstrated the opportunities, even way back then, that came from working with the IEEE and using it as a means of, shall we say, getting the word out and demonstrating what the state of the art was. And just in kind of closing on that, I would add that you mentioned that there were 3 pictures there, or pictures of, if you will, 3 publications. Well, it turned out we felt it was sufficiently successful that in 1980 we again put out a special issue, and last but not least, in 91 we did yet a 3rd one. So there's a set of 3 which I think all of us were pretty proud of, and that was why I wanted to show those or slides of those pictures over there in the IEEE ITS conference, because I felt it was really an early precursor of the role that is being played there even today.
I believe so. Okay, Mr. Saxton, with your long experience, I think very few could have a better data series to make a future projection in our field. So can you please share what are your impressions on the current situation of intelligent transportation? Where are we headed?
Well, I think everybody that works in the area of ITS would certainly agree that ITS, in a sense, is a very broad area. You know, it covers, in fact, the classical areas that we've talked about for years have been traffic management and driver communications, commercial vehicle operations, and advanced vehicle control. So in this very broad area, you know, I think there are a lot of exciting advances that are occurring in each of these individual areas. And I suspect that we would all say that clearly today, automated vehicle control, or if you will, autonomous vehicle control, is probably getting the majority of the headlines. And I'd like to talk about this because this is an area that's dear to my heart. But, you know, before we get into that, let's look at some of the other areas of ITS that we just mentioned and talk about them as well. The thing that I would say is that one of the main features that I like about ITS, and I've always enjoyed as an engineer, that it's really a true systems problem in all of its dimensions. I mean, you have to come at it, if you're really going to be successful, not as individual components, but to come at it from a systems perspective. And of course, systems are broken down into individual pieces, and in that sense, ITS is no different. I mean, there's the actual hardware and subsystems design, there's all the modeling and simulation and optimization algorithms that become important. Today, we're getting a lot of attention in the field of communications, and not just backbone communications, but vehicle to vehicle and vehicle to roadside. In fact, as we look forward, I think in this ITS area, we see a lot of the opportunities for safety improvements to be in the area of vehicle to vehicle communications, as an example. And of course, you know, the control sensor and detection technology, you can go on and here, and I think that the listeners certainly get the idea of what we're talking about or have experienced it themselves. And last but not least, though, I would want to mention that we need to keep our eye on the softer science as well, such as human factors, because the whole ITS program is one that is not going to be successful unless the needs and the constraints, for that matter, that are imposed by the human are dealt with in terms of our systems design. Well, the point I would make in all this is that as we see individual advances in each of these supporting areas, these component areas, and we are seeing them, like, as we mentioned, whether they be in communications or whether they be in modeling or whether they be in optimization theory, as we see those improvements and enhancements, they in turn support the same type of improvements and enhancements overall in ITS. In fact, if I can digress just briefly with a little bit of history, I remember very vividly that there were many things that let's say in the 70s and the 80s, that we hypothesized and said, this is what we would like to do. This is what we'd like to see ITS become. But the technology or the software, the sciences did not support it. And one of the main ones, in fact, was the cost of the technology. For example, I happened to be up in Chicago back in the early 80s, and we were, they were starting to evaluate and demonstrate the first cell phone. And this was in Chicago with AT&T and Bell Labs, and Motorola had built the equipment, and they were demonstrating it to me among others. And I said, hey, this is really neat. This is great. And they popped the lid of the car that it was in, and that whole car trunk was just totally full of hardware and electronics and so forth. And I thought to myself, this is neat, but when are we ever going to be able to get the form factors down and get the costs down and get the technology to the point that we're going to be able to afford that? And of course, the same is true today. I mean, now you look at your intelligent phones and the cell phones and so forth, and you see what has been available in terms of the technology to support the advances in IVH or ITS. And I think that's what we'll continue to see in the future as we see the improvements in the underlying and supporting technology. We will then be able to do more of what we wanted to do in terms of some of the overall system operations. And if you'll permit me, I'd like to just kind of switch gears a little bit as well, because the other part of ITS is not just the underlying technology, but it's getting back to what I said a minute ago about looking at ITS as a system. I think that what is really useful, has always at least been to me, is to think of the ability to deal with the individual components, the idea of what you're trying to control, the ability to get the data from whatever means, the optimization criteria that you can use, and clearly then the control measures that you can use once you decide that you want to try and do certain or make certain improvements to a network or to a corridor or to a signal network. And so it's, as we look to the future, I would say that some of the bigger improvements are still ahead of us, in that we're going to be able to kind of close the loop, if you will, for system control, to the extent that we can get adequate data, characterize networks sufficiently accurately, and get some optimization criteria that we can run in close to real time or near time. Then we have the ability to say, okay, this is what we're predicting as future problems, and we can institute whatever control measures we have, whether they are lane control, or whether it is signalization, timing patterns, or whether it is metering control. But once we can kind of control or close the loop, rather, so that we can model that network in real time and look at perceived changes, it gives us even a better opportunity then to actually institute those controls. And this becomes especially true now that we have a strong population of in-vehicle vehicles with in-vehicle guidance, I'm trying to say, and drivers who are interested in finding the least congested routes and are willing to make alternate choices. And that, I think, is where we see even more and more improvements in ITS implementation in the future.
Mm-hmm. Oh, thank you. What do you think about the current revolution we're living, for example, about transportation electrification or sustainability? What are your thoughts on that front?
Well, certainly this is a whole area that's critical to society, and I think as we learn, especially as we look at the larger environmental issues that are facing society, I think, of course, everyone looks to electrification, and as part of that, we continue as an overall society to look for breakthroughs in electrical storage technology. But I think in the meantime that we're probably going to see more of the electrification aspects taking place probably in the commercial sector and public transportation, where we've certainly seen this in the past. But I think this is an area that is going to probably come along naturally, and it's probably going to be driven as much as anything by, as I suggest, the larger societal issues, and I think ITS is just going to be part of that overall equation of dealing with the needs of society in this respect.
Hi there! We are recruiting volunteers for the ITS podcast. If you like our show and you think you can share some of your time with us, please let us know. Send us an email to ITSPodcast@gmail.com. ITSPodcast@gmail.com. We will appreciate it. Now let's get back to our today's interview. Thank you. Okay, here's the last one. Mr. Saxton, do you believe we will have a predominance of automated transportation in the years to come? For example, private cars. Do you expect them to become automated in the near future, or do you put yourself in the skeptical group and you are more inclined to expect more and more ADAS instead?
Well, Javi, I think I must warn you that I have some strong biases in this area. I mentioned that I came to Federal Highway back in the late 60s, so that seems like a long time ago. But I've been interested and I've supported and pushed for a solid program in automated vehicle control ever since those early days. And I was surprised, if I can go into just a little bit of history here, I was surprised that even in the 60s, there were programs in actually doing some hardware development in automated vehicle control. Ohio State University, as an example, had a program in the 60s. There was a gentleman who was a good friend of mine, for that matter, Dr. Robert Fenton, who was at one point the chairman of the EE department at OSU, who carried on a program and sponsored a program for probably, 5-10 years in vehicle automation. They were primarily looking at lateral guidance, and they were one of the early ones that were looking at wire followers for lateral guidance. But it just demonstrates that there has always been, I think, those who were involved in perhaps looking and seeing what they see as the potential future of automation and who were involved in it. And in the 70s and in the 80s, there's the PATH program at Berkeley, University of California, Berkeley, with people like Steve Schladover and Weibin Zhang that have been involved. Federal Highway has supported automation research well into the 90s, and in fact, in the late 80s and early 90s, there was a whole set of fairly substantial, what were called precursor studies on automation that were supported by the Federal Highway, and did what I would claim, and maybe again I'm biased, but I would claim they really set a strong foundation in looking at some of the capacity improvements, some of the safety issues, some of the human factor problems, legal issues, and that whole body of completed research is available, and it, by and large, is, I think, as useful today as it was probably then. Now, the big difference between what was going on then and what is going on now, in my mind, is there was always the chicken or egg question in terms of implementation. When we looked at fully automated vehicles, I guess we had limits on our forecast as to just how robust future technology and sensor technology and control technology might become, because we did not feel comfortable thinking that we could have fully autonomous vehicles that were operating independently in traffic on their own for some years, or for 20 or 30 years. And I think to some extent this has probably evolved quicker. So the majority of the problem back then was seen as the difficulty in being able to do vehicle control and do it under an automated sense in a mixed environment where you had vehicles operating both manually and automated. But that is that's the huge benefit. That's the big thing that is now happening with the advances in technology that are permitting the autonomous vehicles, and with the also the advances in AI and the advances in modeling and so forth that are allowing, I think, this to appear to be a real reality in the next few years. And I think when that happens, then society is going to be in for a significant taste of the benefits that automation can provide to them, both in safety, in terms of eventually capacity improvements, certainly in terms of if you will, the comforts of that automation can provide in long distance trips and things like that. So I'm a big believer. I think the point that I do want to be stressing here, though, is that there was a lot of research and a lot of development that has gone on over many years, and sometimes that may seem to be forgotten. It may seem that automation is just a really recent thing, when in fact that is not true. And in fact, I again would stress that I see the autonomous vehicle as simply being the means of bridging this gap from a fully manual system that we have today to one that becomes one with mixed vehicles and eventually perhaps fully automated. But it allows us to do that without having to go out and create and build, brand new facilities that would be for automated vehicles only. The point I would come to, though, is that once this transition is made, that where the majority of people who were looking at automation in the past, they saw it having two major benefits. Again, safety, because we know that roughly 90% of most accidents are human related in some sense. They basically result from human error or human limitations. But the other big area is capacity improvement. Now, to get the capacity improvement, today we look at driving on freeways and under really high demand situations. Maybe 1,900, 2,000 vehicles per hour per lane is pretty much the maximum you can expect. And even there, you start getting shock waves in your traffic flow, and you get breakdowns and things like that. But if you can project a fully automated stream of vehicles, you're talking about perhaps 1 second headways, or potentially even better. And a 1 second headway is 3,600 vehicles per lane. So the benefits of automation are there. And I personally see an evolution that goes now from the autonomous vehicle with its ability to offer full automation on a personal basis, but not necessarily giving you the big benefits that you can get in urban areas and urban networks, especially in high demand corridors, that you can get when you eventually get fully automated flow. So I think if we look ahead, we can think of an HOV type facility, and at some point perhaps the population or implementation of fully automated vehicles has reached the point that you could say, all right, we're going to take a lane out of that HOV and we're going to restrict it to fully automated vehicles only. And I think at that point you're going to start seeing some of the major capacity improving advantages of automation. And, that's probably not 5 years away, but I think it is not too many years in the future as automation becomes accepted. So I'm a strong believer in it. I think it's going to be a paradigm shift to society. I think it's going to make major changes in terms of how people set out and plan their trips and the timing of their trips and the benefits from the safety to society. I think automation is, as I say, truly going to be a paradigm shift for transportation and society.
Well, I think many of us are waiting for that future with excitement. Okay, Mr. Saxton, that was it. Our sincere congratulations for your recent and widely deserved award, and thank you very much for sharing your insights with us today.
Oh, Javi, it's my pleasure, and thank you for the invitation to do this. And let me also congratulate you on a really wonderful and successful conference that you had in Las Palmas back in September. And I think it's things like that with the IEEE, especially the IEEE ITS Society, that are important to basically keep this area focused and to spread the knowledge as to what's going on. So thank you again.
Thank you. Goodbye.
Goodbye.
Okay, this is the end of today's episode. We truly hope you found it interesting. But of course, we're open to constructive criticism and suggestions. You know how to find us. You can start at our website at itsp.cicei.com. Thanks. This podcast is sponsored by the IEEE Intelligent Transportation Systems Society, website designed and managed by the Innovation Center for the Information Society at the University of Las Palmas de Gran Canaria in Spain. Soundtrack developed by Rubicon, language advisory by Manuel Arbelo and Professor Sean Williams from Clemson University, South Carolina. Audio edition, post-production, and dissemination by the Institute of Cybernetics at the University of Las Palmas de Gran Canaria. I'm Javier Sanchez Medina from the IEEE ITS Society. We'll be back soon bringing you again the cutting edge of science at the Intelligent Transportation Systems podcast. Thanks for listening and drive safe.